Our first speaker will be Bill Gutowski. Bill is a professor of meteorology in the Department of Geological and Atmospheric Sciences at Iowa State University. His research is focused on the role of atmospheric dynamics in climate, with emphasis on the dynamics of the water cycle and regional climate. Dr. Gutowski's research uses a variety of modeling and data analysis approaches to capture the necessary spatial and temporal scales of these dynamics through the Regional Climate Modeling Laboratory at Iowa State University. He's going to be followed by Dr. Rick Cruse. Rick is a professor in the Department of Agronomy at Iowa State University and director of the Iowa Water Center. He has served on the National Advisory Council for Environmental Policy and Technology for the United States EPA from 2007 to 2009. He was appointed to the Iowa Climate Change Advisory Council by Governor Culver, and he co-authored a report to the governor and the General Assembly titled Climate Change Impacts on Iowa from 2010. Bill, take over.
Thank you, Joe, for that introduction. I want to also acknowledge some colleagues of mine at Iowa State and other places that have contributed to present to you this morning. I also want to thank the organizers for inviting me to come to this very interesting event, which, as many of you know, actually started last night with a wonderful art installation over at Legion Arts. If you have not been over there to see it, I would strongly urge you to go see it. And I mention it in part because one of the themes running through that art installation is the theme of contrast. And that's really resonates quite strongly with what I want to present to you this morning. Contrast and really increasing contrast. The two key messages that I want to leave you with today are that we're going to be seeing, we have seen in recent decades, really increases in both heavy rainfall, but also increases in dry periods. And those changes are actually consistent with our expectations of what the future holds under global warming scenarios. So what we're seeing over the past recent decades actually is very consistent with what our expectations are for the future. And again, a key word behind that is increasing contrast or intensification. We've obviously seen lots to do with floods, but even last year we had a drought. Even though the evidence is much stronger for increasing floods, there is also evidence for increasing drought in the future, and I want to make sure you don't forget that as well, because it's those contrasts that, as I see it, probably present even bigger headaches for the water managers. So why am I saying all this? One of the ways to think about this is to ask how much water can the atmosphere hold? The more water you can have in the atmosphere, the more that can fall out as rainfall. This diagram here shows that one measure of how much water is in the atmosphere for one point in Iowa, but it's representative statewide. Dew point temperature has been increasing over the past 40 years or so. This means that you have more water present, so when it starts to rain, you can start to have an even bigger deluge. It also means that you have to start to pack more water into the atmosphere to get up to that saturation level, so it means that you can end up having longer periods before the rain actually starts to fall, which means you could have more dry periods as well. Sometimes that seems like it's a contradictory statement, but you actually can have both happening, and that's what our best understanding of the processes involved are telling us, that we have longer dry periods as well as increasing deluges, heavy downpours that can lead to flood. So there's more moisture in the atmosphere now than there was on average 40 years ago. But also note that there's a lot of variability here. So that means we can have lots of changes from one year to the next. And that poses big challenges for people trying to manage water. Related to that, of course, is precipitation. And what we see is that if we look back over the past, really over 100 years, we see that, again, there's lots of year-by-year fluctuation. But as I point out here, there's been an increase in the number of years that have water, total rainfall across the state above 40 inches. So the first 70 years or so, there were about 3 years that had that. Past 70 years, there have been 5 years that have had statewide years with precipitation over 40 inches. But I also point out that there have also been an increase in years that have been relatively dry, years with totals less than 25 inches. So again, this issue of increasing contrast. And you can also see that a little bit in this diagram, in that there's a little bit more fluctuation from year to year as you go towards the present and the past. Coming a little closer to home here, this is the same kind of information for Cedar Rapids. Again, a period of over 100 years. And over that 100-year period, there's been about a roughly 39% increase in the amount of rainfall that we have from one year by year. Again, there's a lot of fluctuation from year to year. You can see even more clearly here that that fluctuation has gotten stronger as you go from one year to the next. Again, these increasing contrasts, this intensification of the variability, if you will, of the water that we have available to work with. Even more to the point, we asked how many years have had more than 40 inches at Cedar Rapids. You can see that over the first 70 years there were just 2. In more recent years, 18 years. So a marked increase in the amount of number of years that have heavy rainfall occurring, and obviously all the problems that that poses. Another way to think about it is to ask, how often do we get rainfall that is more than 1 1/4 inches? I mentioned that number because if you start to get rainfall of that amount or larger, and Rick will amplify this more after me, you start to get runoff created. That is to say, water can't get absorbed as easily into the ground. And so it starts to flow along the surface, greater chance of flooding. So what we see again is lots of fluctuation from year by year, but if you also look at this, you see that there are more days in recent years that have had more than 1 1/4 inches of rainfall. Overall, from the beginning to the end of the period, gradual increase. 3.5 days typically, going back 100 years ago, more like over 6 days now, coming up to the present. Again, with a lot of year-by-year variability. If you want to count the number of occurrences, number of years with more than 8 occurrences, so several days with this kind of rainfall, over the first half of this period, there was none. There were none. Whereas in the recent period, there were 9 of these years that had over 8 days. So again, another sign of the intensification of the water flow through our system here, and obviously the issues that that poses. I said this is consistent with trends towards the future. This diagram here shows one way that climate people look at the future. This is what they do is they look at the maximum 5-day period of rainfall in any given year, and they average this 5-day rainfall, the maximum from each year over some time period, usually 20 years in this case, and they've compared distant future as simulated by these computer simulations of the future. This comes from 30 different versions of these models that simulate climate. And they look into the distant future and they compare it with the present. And what we see is that over really almost all the land areas of the planet, you see lots of blues there, some darker shades than others, but over almost all the land areas of the planet, the 5-day precipitation, the maximum amount that you get in any given year, is expected to go up by 15 to 25%. And if you look really carefully, we are, see in the middle of the North American continent where we're located, it's probably on the order of 15–20% increase. So substantial increase expected. So a continuation of the trends that we've been seeing. But I also want to come back to this point about dry. One way the climate people measure dryness is to ask, what are the consecutive number of dry days that you're getting? And again, comparing the distant future with the present. But again, looking at this in terms of a trend that we can think about. Iowa is sort of in a transition area, if you look very carefully there, between places where it's expected to increase or decrease. So we're sort of in a marginal zone. But if you look over the planet as a whole, lots and lots of areas are expected to have increasing dry periods. And so we can't say with as much confidence that we're going to get more heavy rainfall, more dry periods as we are getting more heavy rainfall, but nonetheless there are strong indications that that could well happen. So it's important to keep that in mind, that these increasing contrasts could well be part of our future. They're part of the trends we've seen up to the present. They could well be part of our future. And this is also seen in another diagram that one of my colleagues presented. This is variability of growing season precipitation for Iowa. It's, again, a collection of results from a number of different models. They don't necessarily show the exact same behavior year by year, but the cloud of their behavior as indicated by that colored band, it tells us what to expect. That we expect to have more years with more intense rainfall, but also more years with, the slide says extreme droughts, but certainly more years with less low precipitation. Something again to keep in mind, increasing contrast. So again, I want to come back to my key messages to finish off. That increases in heavy rainfall and drought have both occurred looking over the historical record. They've tended to increase going over the past century. And if you look at what the projections are for the future, those trends are very much consistent with the trends we would expect from a planet where there is global warming going on. This tells us that we have very strong reason to expect this kind of behavior will continue into the future, both increasing heavy rainfall but also increasing dry periods. With that, I will thank you and turn the podium over to Rick.
Thank you, Bill. Thank you again. I appreciate this opportunity. Thanks to the organizers and those in attendance. It is a humbling experience speaking to people with the power that exists in this audience. The event in 2008 definitely changed the physical environment. Probably more important is the question how it's changed the way we think. Because that will impact what happens to us and the infrastructure in the future. Runoff occurs. I will talk a little bit about what causes runoff, and then how management has impacted runoff, and lead into some future likely happenings. Runoff occurs when rainfall intensity exceeds the rate that water can enter soil. Infiltration. That's a no-brainer. It's not rocket science. An infiltration rate is affected by various things. One is the soil pore size. These little holes between soil particles. We've got to deal with this when we're talking about ag situations, because we manage the soil. Those pores influence how fast water moves in. Large pores conduct water more rapidly than small. Sands, you can run water through really fast. The compacted clay that you walk across with real little holes, not so fast. Things in red are things that we can manage on the landscape. Soil texture, that's the sand versus the clay. We can manage the crop that we use because crop influences what the soil is like. We can manage the tillage that we use, which in turn influences soil structure. Soil structure is a little aggregate that creates larger pores for more rapid infiltration rates. Or soil cover. Whether we use perennial covers, whether we use cover crops, whether we have residue left on the surface, those are management aspects that all influence infiltration. And soil water content. A dry paper towel will absorb water much faster than will a moist or a wet paper towel. The same is true for soils. When the soils are wet, they don't absorb water nearly as fast. Better chance for water to run off when it falls onto them. And the other is rainfall intensity, and Bill did not give us a very happy picture of what that might look like in the future. So easy to understand the soil is view soil as a sponge. Everybody knows what a sponge is. A sponge holds water in those little holes and on the particle, or the sides, edges, the pieces, the material in that sponge. The soil is very much the same way. Soil holds water in those pores and on the surface of the soil particles. How we manage that soil, remember, influences pores. Now let's take a look at that sponge, and let's pour water on top of the sponge. Okay, but we're going to add something else. We're going to add a filter to the top, a real thin layer, and to try to understand how that thin layer influences water movement into the sponge, water movement into the soil, and therefore runoff. If we have a coarse screen setting on top of the sponge, something with big holes, pour water on, what happens? It's through the screen into the sponge, and the sponge determines how much water is absorbed, whether it runs off or not. Let's replace that screen with something real, a piece of paper. Paper's porous. We pour water on the paper, what happens? Runs off. Okay, we have something similar happening in the field. The extreme would be, in terms of the paper, would be an asphalt blacktop covering soil. Porous open structure might be something like a perennial vegetation strip. Without cover or with cover, we might have something favorable like we see on the upper left-hand side. With rainfall, if it's not covered, we end up with something that you see on the bottom, water runoff that's prevalent then. Cover is critically important. Just re-emphasizing what Bill said, he was part of this report, increased precipitation, not a good thing for runoff and things we're dealing with here at Cedar Rapids. Okay, so let's look at some numbers, some data. And Bill mentioned the event we had last night. We had some beautiful means of conveying information by pictures. How many people were there last night? Okay, visual works very well in conveying information. Well, when you look at what Bill and I do as scientists, this is not a thing of beauty. But anyway, okay, so what we have here is on the left-hand side, we have the 60-minute infiltration measurement. And on the lower side, we have different treatments. We have on the left of the lower is a silver maple grove. We have a grass filter strip, switchgrass, and then the three on the right are corn, beans, and pasture. The 3 bars for each one correspond to different times of the year that these measurements were made. Which condition allows more water to enter the soil? It's a no-brainer. I mean, it's a no-brainer. It's real. What is most of our landscape covered with? Corn, beans. Okay, pasture can be problematic because you have a lot of traffic out in pasture. Okay, so how has our land surface cover changed in the last 140 years? Okay, this is a lot of stuff on this graph. Let's do one step at a time. Let's take a look at that. This magenta, that bright blue, whatever. That's okay. Well, let's look at the top. That top real bright, light-colored blue. All crops. What has happened to the cropland area in Iowa through time? It's increased up to about 1970, where we're pretty well leveled off. Okay, so now let's go down and look at that red line, corn. Our corn acreage hasn't changed a whole lot since about the 1940s, 1950s. We've seen it bump here recently. Commodity prices will do that. What's happened to our small grain acres? They've gone down. What do we use small grains for as a nurse crop? A lot of times for alfalfa. That's the other that you see in the graph, the top red one is going down. What has replaced the small grains? Soybeans. What does that do when you remember the previous graph? It increases runoff. Okay, now let's go back to the sponge. Let's go back to the sponge. This is not leaning totally on agriculture. That sponge, I don't care what kind of surface you have on top of it, what happens to the infiltration rate when that sponge is full? 0, it doesn't go in. The event that we're having now, we have a full sponge. What was it like in 2008? We had a full sponge. However, those events that you get rapid bursts of heavy rainfall events when that sponge isn't full, then that surface and how we manage has a much bigger impact. So we look at another trial, another set of data. This is from Southwest Iowa. It compares how much water run out of 2 different watersheds. One that was totally corn and the other totally grass. Well, corn is a grass, but it's treated differently in this analysis. The red bar is corn, the green is the grass. On the left-hand axis is the amount of water that came out of those separate watersheds. If we look at base flow is the amount of water that infiltrates, goes to the water table, and moves out of the watershed underground. The far left graph, which one of those 2, grass or corn watersheds, had more base flow? Grass does. More water typically goes in, infiltrates. Okay, the next set of bars over, which one had more surface runoff? That's what we'd expect. Total yield, total water yield, the total amount of water that came out of those watersheds was greatest for corn. See, the other thing that happens if you've got a perennial cover is that during the early part of the season, you've got transpiration occurring. So you consume more of that water that leaves, that moves off into the atmosphere, or both early and late in the season. Let's look at only the top graph here. All scientists are notorious for having a graph that no one can understand. Let's walk slowly. This is pretty important stuff. This is from the Neil Smith watersheds, and it compares water runoff measured through flumes for 4 different treatments on each of those watersheds. One of the treatments, that red line, is for 100% row crop, no till, on the contour. The next treatment is 10% perennial cover, 10% perennial covers, and then a 20% perennial cover. Okay, so let's look at that top graph. On the horizontal axis is 2008, is the time that starts January, February, March, April, and runs into June. And it's cumulative runoff from those watersheds. Let's go clear to the right-hand side and take a look at which one of those treatments had the highest runoff rate, highest cumulative runoff. It was the row crop. All of our data suggests that that would likely happen. And the other ones with the perennial cover had less. But at infiltration rates, we'd expect that to occur. Even more striking is the amount of sediment that's exported. And now we'll drop down to the bottom. That's on soil loss that's exported from those watersheds. How much sediment did we have exported where we had basically any perennial cover? Here to the right-hand side of the graph, lower graph, just about 0. Where we have all row crop, then understand this is no-till on the contour of corn beans. Visual sometimes is better than the numbers. Left was a row crop, the right is the perennial areas. And I think the last data slide that I have is just an illustration from USGS stages, or gauges, the Cedar River annual flow starting about 1900 through 2010. We see more water coming through. Now don't blame ag totally. Because remember the slide that Bill showed about the amount of precip that's occurring. Precipitation is playing a major role. And the events that we're seeing that are major problems are occurring when that sponge is full. I think a bigger issue, and no one has mentioned this at all, is our loss of storage that occurs as we continue to remove soil off the landscape and put it in reservoirs and places we really don't want it. Soil, by weight, will store about 30% when it's drained water. If we remove 5 tons from a given acre of ground in a given year, how much capacity to hold water have we lost? You can do the math. Not only have we lost capacity on the landscape, depending where it ends up, storage facilities, capacities, basins, reservoirs, we're hurt that way too. Concluding comments. Loss of continuous living cover, increasing soil disturbance, and others have increased runoff. It's given. Impacts are greater for smaller events and drier soils. Remember the surface covered, filtered. Much smaller impacts for the larger events and wet soils. Those are the biggies. Water runs off concrete, asphalt, and building roofs. Based on USDA, based on American Farmland Trust, we're losing about 1 acre of ag land per minute in this country due to urban expansion. Extreme rainfall events are increasing. Runoff is likely to increase. Sorry. It's life. Thank you.
Thank you, Rick and Bill, for those presentations. We're a couple minutes after 10. We're kind of ready for some questions. We've got 5 minutes for questions, and we're going to take a break. I'm sure people are ready. Right? You first.
Yeah, Marty, Rick and Dr. Bill, both of your presentations were great. I think one other point we want to make on soils is the capacity of the sponge. Rick, you made a really good point at the end there about as we lose soil, we lose sponge capacity. Also, as we lose organic carbon, we lose sponge capacity. And I think that's an important point that I think we want to emphasize too. Not only the problem with losing it, but the opportunity to rebuild it, and that'll be, I think, an important point.
Thanks for your comment. Other questions? Right here.
Nobody's mentioned the fact that I hear our aquifers, even though we have all this water, our aquifers are actually depleting across the nation. The Ogallala aquifer, we're having to limit the amount of irrigation that they're using down there. So why is that correlation? Why wouldn't you expect the aquifers to hang on longer?
The question is for the video, with all the precipitation and all the water in our rivers and streams, what's going on with our aquifers, our underground water supplies, and how does this impact that?
Well, one way to think of an aquifer like the Ogallala is it's like a bucket with a spigot on the bottom. And if you open up the spigot, you're draining water out of it, which is what you're doing when you're withdrawing water for irrigation. The water level will go down unless you start replenishing it. But if the amount that you start to put into the bucket at the top is less, then the net balance is going to be that you're drawing it down. That's what's been happening. And a deep aquifer like the Ogallala gets replenished very slowly. I'm not an expert on this, but my understanding is that a lot of the water that's in an aquifer like that is hundreds and maybe even thousands of years old in terms of when it was last on the surface. So that's a sign that it actually moves very slowly through that system. And so if you start pumping water out pretty rapidly for irrigation, it's inevitable that you're going to draw it down.
Actually, the Ogallala was filled with glacial melt. And there's one other aspect about that. As you add to the corn price, you can buy more expensive land, you can spend more on genetics, you can pump water from deeper layers. So we're elevating our extraction also.
By the way, that land used to be in winter wheat in that aquifer, and now they're planting corn.
We've got time for one more question before the bathroom break. Question, any thoughts on tile drainage and impact on natural hydrologic response?
Yes.
It's part of a broader, very interesting question, which I don't think we've really, at least in our research community, addressed very clearly yet. It actually goes back to the issue of irrigation in the Ogallala as well. We have changed the status of the landscape across the whole middle part of the country. We've taken places that used to be pretty dry, farther west, and we've been pumping water onto the land surface through irrigation. We've taken places like this that used to be fairly wet, and we have made the land surface drier, and we have changed the whole nature of how water moves through the system with the crops we plant. That has impact on the weather as well. People have done a little bit of study on that. There needs to be much more study because there's actually feedbacks that plays into. Maybe Rick wants to add some more.
I'll go back to the sponge. If the sponge is full, it sits there for 2 days, and you get another 2 inches of rain, what happens to that 2 inches? It runs off, and it runs off the surface fast. If you have tile drains in, and those tile drains are running for 2 days, most of our tile drains over that period would give you about a ½ an inch of storage capacity. It would remove that much, but it removes it over a 2-day period. So it does add to the river flow, but much more gently than it would with off-surface runoff. You get 2 inches of rain, a lot of that's going to run off, but you have reduced the quantity that will run off in that 2-day period by the added storage capacity put in the ground.
We've come to break time. Pete, when do you want people to come back?
About 10 minutes.
About 10 minutes. Please join me in thanking Rick and